the gasoline, you know that the amount of emission that we are putting, or the amount of energy that we are putting on this and the emission resulted, and considering the economic value, you will find that the gasoline has a higher economic value, of course, than the asphalt that we're using. Then you will find in this case here that the gasoline is more important when it comes to this than the asphalt or the asphalt binder. We cannot look into the construction as a phase by itself. It has to be looked at from a holistic point of view. And looking into the life cycle assessment of the pavements or of the asphalt pavement, there is 5 phases, as you know. The first one is the material production, and the second one is the construction. The third one is the maintenance and rehabilitation. Then the fourth one is the use, and then we have the fifth as the end of life. As you look here, the construction one is around 1.2%, but the majority of the energy consumed is during the use of the pavement, which is the vehicle that it's using this pavement. So in this case here, you will find that the construction, although it is very low percentage in the whole life cycle assessment at 1.2%, it has a lot of impact on the use phase. If the material that we are building, or if the pavement that we are building, it's not as good, or the quality control is not as good, then we have to do some rehabilitation in the future, and that will definitely going to impact the congestions, the delay, and so on. And if the pavement that we are building is rough, then we're going to be having more oil used, or more fuel is used by the vehicles. Therefore, it's going to be having an impact, significant impact on the other phases. That's where the importance of the construction phase coming from. If we take the use phase and the end of life phase out of this, we'll find that the construction phase contributes around 14 to 15% of the life cycle assessment, and that's a very significant number, as I said earlier. Now, how does during the how the construction impacting the environment? If we are looking at the different equipment that we are using during the construction, each one of them it will affect it's affected by the energy that it's producing, as well as the impact on the environment. So if we pick one of these equipment here, such as a paver, we'll find that the horsepower range from 125 to 225, and the fuel consumed is 35 to 50 gallon per hour, and the emission is 90 to 136. If we look at the vibratory roller, we'll find that the horsepower is maybe a little less, and the fuel consumption is a little less, the range, but we have the emission is much higher. This is very important for us to know where the energy is spent or consumed, and where's the emission is coming from. And that will allow us to fine-tune some of these equipments to make it more sustainable by reducing or limiting use, or try to optimize the use of some of the equipment in order to make this better from first an energy, which means economy, as well as the emission that it is, or the greenhouse gases that it goes into the environment. So if I look at the example of equipment contribution here for a highway project, you can see that the dozer is the one that it's used most of the energy, and of course it will produce the highest global warming potential. And if you look at the paver, it is using the lowest energy among all the different equipment that it's used in the construction. This is by itself will give us an idea about where most of the energy is going and where is most of the emission is coming from, and that will allow us to optimize during the construction process what we can do in order to reduce the energy use and also reduce the emission. This is a case study where the construction activities for a high volume road, and again, if you look here, because the paver has been using less energy than other equipment, you can see here that the full depth, or 12-inch full depth of hot mix asphalt, has been using less energy than, for example, the earth excavation, which is going to be requiring a lot of use of the equipment in order to accomplish the job. The second point that we'll be discussing here, the impact of construction on surrounding area, and I will be discussing the first 2 points a little further here, which is the emission from the equipment exhaust and the airborne particulates from the construction operation. But if we look at the noise, the pavement construction is a noisy process that results from the excavation, movement, processing, and placement of large volume of materials using large, powerful machinery. The resulting noise from the exhaust stacks, plant site operation, earthwork construction, material hauling, and so on can be irritating at best, and potentially it can be hazardous to the health, where people can be disturbed by losing sleep, or sometimes it can be affecting their stress level. So noise is an important thing to look at. The other one is to look into the impact on the local traffic, residents, and business operation. For the construction work, often it results in a reduction in the roadway capacity and throughput due geometric restrictions, reduced speed limits, temporary closure, detours, and other congestions-induced activities. Of course, this will be parallel with significant costs that it will be associated with the construction-related traffic delays, and of course the work zone areas, including the time and reduction in the productivity of the users of this highway. And of course, that will be reflected also on the fuel consumptions of these vehicles. The fifth point here, which is also very important, which is the construction in streams, wetlands, and environmentally sensitive area. Temporary erosion and sedimentation control plan or stormwater pollution prevention plans may be needed when we are doing a highway project that includes earthwork removal. However, even on project sites where best recommended practice or requirements are followed, sometimes we have sediment that it continue to be discharged at a concentration dangerous level. Hence, effective pest management practices to prevent erosion and to reduce the risk of costly sedimentation control measures and environmental damage are part of a sustainable pavement construction. If we look into the exhaust, which is the first 2 points I mentioned, the exhaust emissions on local air, the Clean Air Act requires EPA to set the national air quality standards for particulate matter and other pollutants that are considered harmful to human being and to the public health and to the environment. This is including the hydrocarbons or the non-methane hydrocarbons, the carbon monoxide, nitrogen oxide, sulfur oxide, volatile organic compounds, and particulate matters, as well as the carbon dioxide. These are coming from primary particles as well as secondary particles. Primary particles such as the dust that we have in the roads, or what we're getting, the dust also from unpaved roads. Secondary particles, these are emitted from the equipment, cars, tailpipes, combustions of the fuel, including the construction equipment. The EPA standard on engine limits has been really helping in reducing the emission in the environment. So if you look at the first figure here, this is giving the different tiers that I'm going to be explaining in a minute in the next figure here over the years. So this is from almost 1995 to 2015. So if you look here, the reduction that we have on this column here, we have the different horsepower ranges that we have for the non-road diesel engine that it's analyzed. If you look at this figure here, it shows the particulate matters as well as the non-methane hydrocarbons on the x-axis and the particulate matters on the y-axis. And you can see for two cases here, or two range of horsepowers between 75 and 130, kilowatt and between 450 and 560. And you can see here tier 1 is the late 1990s, and by early 2000 you can see the big drop that we have on both of these, the PM and NMH and nitrogen oxide. Now between early 2000 and late 2000, although the particulate matters kept constant at the thresholds, you will find that the non-methane hydrocarbons and the nitrogen oxides have been reduced. And if you look now on the tier number 4, which is late now, we're talking about 2015, now this has become very restricted. If you look at the example here at the bottom, this example, I think you cannot see the x-axis. The x-axis represent the years. So the first one here is 1990, this big column, and the last one is 2014. And you can see a very significant reduction, almost by 5-folds, of the PM emission that is coming from the diesel paver, that it has a 600 horsepower. So this kind of reduction is very significant. So actually in construction, we are doing some, I would say, some good job in sustainability when it comes to the equipment, and this is an example. But what we are talking about here is what we can do during the construction process itself in order to improve the sustainability. A good example here is the example from California by the California Environmental Quality Act, that they proposed the construction emission thresholds to identify critical projects to calculate emissions and require mitigations. These emissions or these calculations are based on databases or some software as needed. So the mitigation of the construction activities is required when the emission thresholds are equal or exceeded by the fugitive and or combustion's emission. In the case of daily, which is the first column here, for construction projects expected to be completed in less than 90 days, exceedance of 137 pounds per day, the thresholds required that we do as standard mitigation measures. In the case of the quality tier 1, which is for construction projects that it's lasting more than 1 quarter or 90 days, exceedance of the 2.5 tons per quarter threshold requires standard mitigation measures and best available control technology for construction equipment. If implementation of the standard mitigation and best available control technology measures cannot bring the project below the threshold, then off-site mitigations may be necessary. And for the third one, which is the case of the quarterly tier 2, for the construction project that it's lasting more than 1 quarter, exceedance of the 6.3 tons per quarter threshold requires standard mitigation measures, best available control technology, and implementation of a construction activity management plan and of off-site mitigation. Please notice here that when we are talking about the best available control technology, it's kind of like a little more restrictive from the reasonable available control technology, but it's kind of not reaching the same level as the lowest achievable control technology. So with this example here, I think we're going to be moving to the third point, which is the construction management and sustainability, and I will turn it to Hassan. Hassan?
All right. I will be wrapping up the construction section and also the webinar with the last 2 links that we thought it's important for the construction, the effect of construction practices and on the pavement sustainability. And first of these links is related to construction management and sustainability. An initial introduction has been made to this by the accelerated pavement construction at the beginning of this webinar, and I will mainly talk about the effect of construction practices on the work zones. And we know that construction work zones can cause user delays, increased fuel consumption, and compromise roadway safety. And there are, of course, indirect economic and environmental impacts resulting from construction activities due to reduction in roadway capacity and delays. Some nationwide statistical figures related to highway construction zones, and in the last decade, one of them is coming from US DOT almost 10 years ago. Highway construction zones accounted for 24% of non-recurring congestion, equivalent to 482 million vehicle hours per year. And in a more recent study, and this one coming from 13 different states and more than 3,000 work zones, and indicated a loss of 60 million vehicles capacity per day based on this study. So therefore, we have to do something about this, and in an FHWA study in 2007, there are several strategies recommended for construction sequencing and efficient work zone management. The objective here is that they enhance or accelerate the production, at the same time minimizing the impact of the work zone on the users and agencies. So among those strategies, the first one is establishing, of course, performance goals and measures for work zones. And there are some nice examples of this in Europe and in some states in the United States. And one example is from Netherlands, and they is already in practice now, is the target work zone delays should be less than 6% of all traffic delays in the Netherlands, while this number in the United States right now is around 10%. And the second strategy was incorporation of lane road closure analysis strategies during the project planning. And those analysis strategies are basically part of some of the traffic management programs. And some examples of those programs are FHWA's Quick Zone for work zone delays, Caltrans pavement rehabilitation software, CA4 PRS, and Dynasmart programs that can help for construction sequencing and as well as mitigating the work zone delays. And third is implementing those strategies, best available strategies or the strategies recommended by those programs during the construction, and finally implementing intelligent transportation systems to facilitate the work zone management. And those strategies can regulate traffic speed and volume by advising drivers and providing alternative routes or modes. And some of the components of ITS may include dynamic message signs, radio channels, portable signs, portable trailer, variable work zone speed limits, speed warning systems, and etc. Now the question is recognizing the impact of work zone and construction sequencing. And the question is, how do we quantify those impacts? And we talked about some of the programs that can do this job. Basically, the idea is to quantify the energy and emissions and user delays and economic impact of construction practices, which will result in traffic delays due to construction activities. And this is a phase often ignored in payment LCAs because of the complexity of the problem, and we have to calculate the impact on the environment associated with the traffic delays. And there are basically tools to do this job in two different ways. First, you need a traffic simulator to estimate driving schedules under the changing roadway capacity. And second is the vehicle emission software to be able to calculate, quantify the environmental impact from the changing roadway capacity and then traffic patterns. And some of the variables that needed for the vehicle emission simulators are vehicle-related variables. Those are vehicle types, fuel type, time and geography, and road-related parameters, including road type and geometric design features. And some of the available programs for vehicle emission simulations is EPA's SMOOTH program, and it's an emission modeling system for mobile sources, and it's recently being used in many different applications of payment LCAs, and it quantifies the energy consumption of different types of vehicle under different conditions, and it has an inventory of 120 plus emissions. And another EPA program, non-road, is the emission modeling system specifically for non-road equipment, including construction equipments we use in highway construction projects, energy consumptions, and the limited inventory of emissions to air can be obtained from EPA's non-road program. And what do we really accomplish with those programs is many different advantages of those programs, in addition to construction equipment inventory and predicting the congestion and work zone